Welcome to CATS Tutorials, and in this video we're going to be doing practice problem 2.15. Given this network, we are asked to find RAB and I which is the current which is supplied to the rest of the circuit, and RAB is the equivalent resistance at these terminals A and B. So to start here, we have to identify elements which are in series or parallel and find a way to reduce this so we can find I. And also, reducing this network will give us RAB. So let's start with finding the equivalent resistance at these terminals. So you'll see that these two resistors, 24 and 10 ohms, share that top node, but cannot be qualified to be in series. Also, this node is shared between 20 and 10, but they're also not in series. This node is shared between 20, 30, and 24, but they're not in series. This node is shared between 30 and 50, but they're not in series. So all of these resistors share at least one node, but are not in series. And neither are they in parallel. So they are neither in series nor parallel. So what do? We do a Y delta transformation. If you can look at this part of the circuit, it forms a delta. This is simply a wire which you can reduce to just a single point. So you can just reduce it to something like this. So this top part can be reduced to just a single point right there. It's just a wire which has been extended like that. And so up here, we have a delta network. And this delta network can be transformed to a Y network. And from this Y network, we can solve the rest of the circuit and then find the equivalent resistance. So let me show you a trick which I use to remember how to find the resistors in the Y network. So these are labels which I put on a delta network, just a random delta network. And so if you take the delta network and draw a Y in between, to find this resistor, for instance, R1, which I labeled as R1 here, here's what you do. You look at the two resistors which it's found between. So in this case, that's RB and RC. Then you multiply those two at the top, RB and RC. And then you add the rest of the resistors which are present in the delta network. So you basically add all of them as the denominator. As you can see, for all the others, the bottom part is the same. You just simply add all the resistors in the delta network, which are RA, RB, and RC. So you add all of them. And then at the top, you multiply whatever resistors the element you're calculating is between. So in the case of R2 is between RC and RA. There you have RA, RC. R3 is between RB and RA. R3 is between R. And that's just a trick which I use to remember how to calculate these. So let's go ahead and calculate the actual values of R1, R2, and R3. So if we add this to this network, we'll redraw the circuit into its Y equivalent after calculating the values. So let's continue and calculate the values quickly. So we have R1, which is over here, R1, and it's in between 20 and 24. So 20 multiplied by 24, and then divided by all the resistors present in the delta network. So 24 plus 20 plus 10, right? And R2 is equals to R2 is over here. So it's between 20 and 10. It's between 20 and 10. And we divide by the same thing, all the resistors in the network, in the delta network. Finally, we have R3, which is over there. It's between 24 and 10. So it's between 24 and 10. Then we divide by all the resistors in the network. So all you have to do is just simply punch this into your calculator, and you should find for R1, you should find that its value is, let me just quickly punch that in the calculator. So R1 will be 20 multiplied by 24 divided by 24 plus 20 plus 10. So after calculating, these should be your values. These should be your values which you find, right? So let's redraw the new circuit with the new Y network. So this is what we have. We still have the 13. We haven't done anything to that. Now here, R3 we found to be 4.444. Here we have R1, which we found to be 8.889. And here we have R2, which we found to be 3.704. And the rest of the circuit, we have 30 ohms there. We have 50 there. And the terminals A and B. So now we actually have elements which are in series and parallel. So as you can see, the 13 is in series with the 4.444. So you can just add those. So 13 plus 4.444. And you have this in series with that. So you can add that as well. So 30 plus 8.889. Then you can also add this and that because they're in series. Right, so you add 50 plus 3.704. And as you can see, the result of these two and the result of these two share two nodes, which means these two results are in parallel. So let's just quickly add these up. So 13 plus 4.444. And that gives you 17.444, and this is 38.889, and this is 53.704, right? So these are the results, and these two results are in parallel. So just saying 38.889 multiplied by 53.704 divided by 38.889 plus 53.704. Calculating that quickly, which is the parallel connection of these two, like these two sections in parallel. That's why we're doing all of this. So 38.889 multiplied by 53.704 divided by 38.889 plus 53.704. And the answer is 22.5556. And let's draw the new circuit. So we replaced all of this with 22.5556. So drawing the new circuit, we have 22.5556 ohms here, and the result of these two, which is 17.44. So we have 17.44 in series with 22.5556. So 17.444, which means RAB, which is the equivalent resistance at terminals A and B, is equals to 17.444 plus 22.5556 is the answer. So you're going to say 22.5556 plus 17.444. And the answer which you get is 39.9996, which is approximately equals to 40 ohms, which is what's written in the textbook. Also, if you want, you can also form a wire network on this side of the circuit. Now, this side of the circuit gives square numbers, unlike these ones here. You get much more friendly numbers to work with. That is also an option. So there isn't one way to solve this. Just try the second method, which is from this side, and see if you get the same answer.